In this video, I want to talk about the finite state machines. So this is, I would say, the most important topic that I'm going to cover for the sequential logic circuits. So I highly suggest you pay close attention to everything that I'm saying in this video. So finite state machines, or FSMs, consist of several components. So since it's a synchronous sequential logic circuit, we definitely need to have state registers or flip-flops. So these are being used to store the current state of the system. So if you remember from before, the basic design that we used for the flip-flops or the registers was something like this. We had a rectangle, we had the clock that was signified with this triangle, and then on the left side of this state register we have S prime, which represents the next state of the system, and we have S on the right side, which is representative of the current state of the system. So if we consider this as a simple flip-flop, the next state would be connected to the data input, and the current state is the Q output of the flip-flop. If we have a bunch of flip-flops, we have basically several data inputs which are connected to the next state of the system, and we have a bunch of outputs, Qs, which basically show the current state of the system. So this is the convention that I highly suggest you follow in your design, considering the next state to be coming from the left side and the current state to be going out of the register from the right side. So at every clock edge, what happens is that this next state will be stored in the flip-flop and then becomes the current state of the register or flip-flop. So that is the major component of the FSM, registers, because as we said before, without registers, basically our circuit is not considered a synchronous sequential circuit. There are some other components too that are, you might say, optional, because that all depends on the design of the circuit. So we have two combinational logic components. One is the one that computes the next state of the system, and one that computes the output of the system. So I show them like this. We have this combinational logic circuit, which is used to basically calculate what the next state of the system needs to be. And then we have this output logic system, which basically calculates what the output of the system needs to be. So let's just take a look at one basic example. Let's just say we want to design a digital clock. So this next state logic calculates what the next time would be, and this output logic unit calculates what you need to show on the display of the digital clock. And at any given state, the current state is being stored in some flip-flops or registers. So now, based on these components, we can have two different types of finite state machines. I will go over one of them in detail in this video. In the next video, I will go over the second one. So these two types of finite state machines mainly differ in the output logic unit. So let's just go over these two one by one and see how they are designed in general. So we have the Moore FSM and we have the Mealy FSM. So let's just go over the definitions first. So for the Moore FSM, the outputs depend only on the current state of the system, while for the milli FSM, the output not only depend on the current state of the system, but also they depend on the inputs too. So if I want to put these two definitions into some generic designs, these are the representative designs of these two systems. For the more FSM, we have a set of M inputs that are connected to the next state logic unit. They create a set of K outputs, which will be the next state of the system. So these K outputs coming out of this combinational logic circuit will be fed to a bunch of registers or flip-flops. At the edge of the clock, signified with this triangle, they will be stored in the flip-flops. So now we said that for the sequential circuit, the state of the system not only depends on the input at the current time, but the previous state. So that's why we have this feedback path that connects the output of the flip-flops to the input of this combinational logic that we use for calculating the next state. So that is the feedback path that we have. And if you look closely, for this cyclic path, we have registers in the path. So that makes this circuit to be considered as a synchronous sequential logic circuit, not an asynchronous. So now for the more FSM, what happens is that depending on the current state of the system, we calculate some outputs. And as you can see, these outputs are only created by this combinational logic circuit that its inputs are the current state of the system. So now let's see what happens for the milli FSM. For the milli FSM, we still have M sets of inputs. We have this combinational logic unit that helps us calculate the next state. We calculate these K next states. And then we use these registers to basically store these states in the system. And then we have the current state of the system that are fed back to the input logic unit. However, for the output logic unit, what we see is that to calculate the outputs, not only we have the current state of the system, but also we have this path that is directly fed to the output logic unit. So if you look closely, this does not create a cyclic path because we start from the inputs and we go to this output logic unit and then we create the outputs, right? And remember, in none of these combinational logic units that we have a cyclic path. So they are pure combinational. We have a bunch of inputs, we create a bunch of outputs without any cycles inside them. So as you can see, the main difference between more FSM and the milli FSM is in the fact or in the procedure that we follow to calculate these outputs. For the more FSM, what we use to calculate the output is only the current state of the system. For the milli FSM, not only we use the current state of the system, but we also use the inputs as well. So this is their difference generally. When it comes to design, we see that generally speaking, milli FSMs are a bit simpler than more FSMs. So you can think of it like this: more FSMs usually are more complicated or contain more elements. But we will go over more examples later on as well. So for now, I'm going to focus on the design of more FSMs. So let's just go over one simple example. This is an example that you are dealing with on a daily basis, and that is a traffic light. So we have in this example the design of a traffic light in mind. We have two streets. We have the Academic Avenue, and then we have the Bravado Boulevard. And we want to design a very simple traffic light to be able to control how people or cars move in this cross section. So what we have in mind is we want to give preference to the Academic Avenue. So what happens is that when you start the system from the beginning, the Academic Avenue is green. That means that people can pass. And when we have no traffic in the Academic Avenue anymore, then the Bravado Boulevard is green. So to be able to record the state of this cross section, we need to create a sequential logic circuit. But how can we detect the traffic? We have two traffic sensors. We don't concern about how these are designed. We only consider them as two input for our circuit. So we have TA, which is basically the traffic sensor for the Academic Avenue, and we have TB, which is basically the traffic sensor for the Bravado Boulevard. So whenever TA is 1, that means that we have traffic in the Academic Avenue. Whenever TA is 0, that means we don't have any traffic in this street. The same is true for TB as well. TB being 1 equals traffic. TB being 0 equals no traffic. So one thing that you can consider right now is that instead of considering TA to be 0, we can also say when TA bar is 1, right? So these two are completely equivalent. So TA being 0 or TA bar being 1 are completely equivalent. The same is true for TB as well. TB being 0 or TB bar being 1 are completely equivalent. So we use both of these interchangeably. So pay close attention. So based on these traffic sensors and their value, we control some lights here. We have LA, which is basically the set of traffic lights for the Academic Avenue. It has 3 colors, green, yellow, and red. And we have LB, which is the set of traffic lights in the Bravado Boulevard. And again, it has 3 colors, green, yellow, and red. So the general description of the problem is that when we start the system from the beginning, LA is green, LB is red, and while this is the situation, we check the value for TA, basically the traffic in Academic Avenue. As long as we have traffic in this street, this is going to be the case. As soon as TA becomes 0 and TB becomes 1, then we go and to an intermediate step. We make LA to be yellow, while LB is red, and then after some time we change LA to red and LB to green, and then while LB is green, we check for the value for TB. As long as we have traffic in TB, or when TB is 1, we stay in this state unless we have TB to be 0 and TA becomes 1. So in this case, again, we go through an intermediate step. LA is still red, LB becoming yellow. And then after some time, we go to LA being green and LB being red. As you can see here, this definition or this description of this traffic light is very simplistic. So we basically don't have any time for each one of them individually. What we have is basically we gave preference to the academic avenue first, and then as long as we have traffic here, we don't change the light, right? So this is not something that is usually practiced in reality, right? But for our case, since we want to start from a very simple example, and then we, if we wanted to, we can make it more complicated. We start from this very generic and basic description of the problem. So now based on these, we need to follow a 7-step procedure to design the more FSM for this simple circuit. Of course, conceptually speaking, if I ask you how you can design such a thing, you probably don't think of 7 steps, right? Because the concept is very familiar to you. But keep in mind that you want to make some set of circuits to basically implement what you have in mind. So the circuits don't have your mind, right? So you have to translate your idea, your abstract idea, into something that can be implemented using a bunch of circuit elements and flip-flops. So let's just go over these 7 steps one by one. So the first step is to identify inputs and outputs in the circuit. So this is something that we did from the problem description. We know that we have 2 traffic sensors, and then we have 2 traffic lights. And based on the values of the traffic sensors, we are basically controlling the traffic lights. The next step is to sketch the state transition diagram. This is something that I did in the previous slide in general terms. We will go over it in more details at a later slide. Then the next step is to write the state transition table. Step 4 is to select the state encoding. Step 5 is to rewrite the state transition table with the state encoding and also write the output table. Step 6 is write Boolean equations for next state and output logic using sum of product, product of sum, K-maps, and etc. And then finally sketch the circuit schematics. So from all these 7 steps, if I want to go one by one, there are some that you already know how to do. So one thing that you may say you know how to do is to identify inputs and outputs. What is the other one that you may know? Step 6 is something that you have already seen before. So going from a truth table into a Boolean equation using sum of product, product of sum, and K-maps. And finally, step 7, sketching the circuit using the Boolean equations is also something that you know by now. So the emphasis will be on these steps 2 from 5 here. So let's just go over each one of these in steps one by one and see how we can go from the problem description into a schematic of a circuit that basically performs whatever we described in the problem description. So the first step was to identify the inputs for our circuit. So assuming that we have our circuit in a black box, obviously since it is a synchronous sequential circuit, we need to have the clock. So that is a given. We had TA and TB, basically the traffic sensors in the Academic Avenue and the Bravado Boulevard. So these were the inputs. Also, we have this reset input, which basically gives us the capability to reset our system at any given time that we want, right? And then we have two outputs. We have LA and we have LB. Basically, LA is the traffic light in the Academic Avenue, and LB is the traffic light in the Bravado Boulevard. So since we don't know how many lines we need to control the traffic light, I just put it like this, with this slanted line. That basically shows that it is possible that these are more than one lines of output. But for the rest, we know that they are only one line. We have only one clock, one sensor for the Academic Avenue, that is either 0 or 1. The same for the Bravado Boulevard, and also for the reset, we only need one line of input. So now that we know this, let's just go over the state transition diagram. So for the state transition diagram in more FSMs, we label outputs in each state, and the way that we represent a state is by circles. So we draw a circle, we give it a name, and that will be one of the states that we have for our circuit. As for transitioning between different states, we use arcs to represent those transitions. So we start from the default or the preferred state of our system, in which LA is green, LB is red. And that is something that was there from the problem description. Also, we said that anytime that we reset the system, we basically go to the preferred state. So we have this arc that comes from outside. You can think of it as, let's say, this switch, right? That you basically push it. So anytime this reset happens, you come to this state. So now let's just go over through the possible states that we can have and complete this state transition diagram. So we start from state 0, I call it S0, in which LA is green and LB is red. So now we need to see what is our next state depending on the inputs that we have to our system. So when we are at a state 0, that means this path is basically open and people can go back and forth, but this one is basically closed. So when we are at this state, we check TA to see if we have still traffic in this path. So depending on the value of TA, we either keep the light LA to be green and LB to be red, or we start the transition process. So that means that if TA is 1, or if we have traffic still in the Academic Avenue, we stay at the same state. So this is one arc that we can draw. When TA is 1, we stay at state 0. So this is the first transition that we have. What about when we check TA and it is 0? So that means that there is no traffic here. Then we can start the transition to go to the next state. Keep in mind that we don't check TA and TB both at once, right? Again, since we want to have a very simplistic example, we said that we only check TA or TB at individual states, not checking them both at once. So since we gave preference to the academic avenue and we always check TA, it is understandable that we may have traffic in TB. So we start the transition process. So when TA is 0, we go to the next state. So this is for when TA is 0 or when TA bar is 1. Both of them are valid because both of them say the same thing. So when this is the case, we go to a state 1 in which LA becomes yellow, LB is still red. So now in this state, do we need to check for any other input? The answer to that is no. Again, based on the simple description of the problem, we don't have to check for any of the sensors because we already assume that we have some traffic in TB. So this state automatically goes to the next state. So let me just redraw this circle, make it more circle-ish. So this is the circle that we have for the next state. This is S2, in which LA becomes red, LB now becomes green. So now the street light in Academic Avenue is red. So that means that there is no traffic going through this path. So no traffic going through this path, but we have traffic going through the Bravado Boulevard. So now when we are in this state, we only check for the value of TB. Depending on the value of TB, we either stay at this state or we go to the next state. So what should happen? So we stay in this state when TB is 1. So when TB is 1, we stay in the current state. So we stay here as long as there is traffic in the second path. If there is no traffic, we start the process of transition. So when TB bar is true, or just simply TB bar, right? Because having TB bar here, that means that this arc only happens when TB bar is true. So that is the condition for this arc to happen. So these two are also equivalent. If this is the case, we go to the next state. I call it S3, in which LA is still red and LB becomes yellow. So that is a transition state. So without considering any inputs, what we can do is that we wait some time here, and on the next edge of the clock, we go to the initial state that we had, which is S0, in which LA is green and LB is red. So let's just recap. We said that to create the state transition diagram, we represent each one of these states as circles. We put some name for them, and then we show the outputs of each one of these individual states inside those circles. So for example, for state 0, LA is green, LB is red. For state 3, LA is red, LB is yellow. And then we said that to transition between these states, we use arcs. So any arc that is dependent on some condition or some input, we put that condition or the input on top of it. Any arc that is not dependent on any input, we just simply provide the arc. And that means that whenever we are, for example, whenever we are at state 1, we definitely go to a state 2, right? Because this arc is not dependent on any inputs. So this change happens on the next edge of the clock. So for the conditions, we said that whenever the value is supposed to be 1, we just put it by the input itself. So we can either write it as TA equals 1 or just simply TA. Or whenever the condition or the input needs to be 0, we just represent it as TA equals 0 or TA bar equals 1, or just simply we can just say TA bar, which is representative of TA bar being 1. So when the condition on the arc is true, that means that the arc can happen. So now that we have this state transition diagram, the next step would be to convert this into a state transition table. Because remember, we want to create some truth tables based on which we want to write Boolean equations. So by this state, still our design is too abstract and cannot be directly implemented using logic gates or registers. So we go step by step to get a truth table that we can use to come up with the Boolean equations. So based on the set of inputs and the current state, we can know what our next state would be. And that is the basis for creating the state transition table. So we have the state transition diagram. And then we have the set of inputs TA and TB. And we use that to create this state transition table. So each arc in the state transition diagram is represented with at least one row in the state transition table. So except this one, the reset one, we don't represent it in the state transition table. So let me just write it here. For every arc in the diagram, except the reset, we have at least one row in the state transition table. So this is very important. At least one row. So not necessarily only one row, at least one row. So we will see later on examples for which we need to have more rows to represent one arc. And that all depends on the condition that we have on the arc. So now based on this, going from the state transition diagram to the state transition table is very straightforward. We start with a state. So it is simpler to start from the first state that we had. So we start from state 0, then we go over these arcs one by one. So what happens if we are at the state 0 and TA is equal 0? Let's just go for this first, right? Because this is something that I put as the first row. But it doesn't matter. You can go with TA being 1, 2. And that's fine. So as you can see, this arc is only dependent on the value of TA. So for this arc to happen, TA needs to be 0 or TA bar needs to be 1. So we have TA 0. And since it is only dependent on TA, that means that the value for TB is don't care. So when we are at the state 0, TA equals 0 and TB is don't care, what happens? What is our next state? As you can see, this arc connects us from state 0 to a state 1. So that means that the next state, or S prime, is going to be S1. Now let's just take a look at this arc. We are at the state 0, TA is 1, TB is again don't care because this arc is not dependent on TB. What happens? We are at the state 0, TA is 1, TB is don't care. As you can see, this arc connects S0 to itself. So that means that the next state, when this condition happens, or when this arc happens, is going to be S0 itself. Now, we go to the third arc that we have here. Again, the order of considering these arcs is not important. As long as you account for all of them except for this reset, it is fine. So for this arc to happen, we need to be at the state 1. And as you can see, this arc does not depend on any of the inputs because we didn't put any conditions on this arc. So for this arc to happen, the only requirement is that we be at the state 1. So if we are at the state 1 and A and B, TA and TB are both don't cares, what happens is that we go to a state 2. So this row is representative of this arc. Again, we are at the state 1. The values for TA and TB don't matter for us. And we go to a state 2. So now we are at the state 2. Let's just see what happens. What should happen? So we go from a state 2 to a state 3. That happens when this arc happens, in which TB bar needs to be 1. And again, since this arc is only dependent on TB, that means the value for TA does not matter for this arc. So when we are in S2 or a state 2, TA is don't care and TB is 0. We go to a state 3. Now for this arc, when we are at the state 2 and TB is 1, we remain at the state 2. Again, the value for TA is not important for us. So we have S2 at the current state, TA to be don't care, and TB to be 1, which makes our next state to be S2. So we stay in the same state. And now finally we get to the last arc, which connects S3 with S0. This last arc doesn't depend on any conditions. So both TA and TB are don't cares. So we are at the state S3, TA and TB are don't cares, and our next state would be S0. So this is a very simple step to go from the state transition diagram to the state transition table. And as you will see later on, is that designing an FSM consists of several steps, but these steps are usually very small, so we change things incrementally, right? But you need to keep all of these steps in mind, and you cannot change the order of these steps. Otherwise, you basically end up at a dead end that you don't know how to proceed from them. So this is how we go from the state transition diagram into a state transition table. Again, keep that in mind, that for every arc in the diagram, except for the reset one, which we don't consider in the state transition table, we have to have at least one row in the state transition table. So this was our next step. Now, let me just quickly go back. Now we have a table that resembles a truth table. Remember, we need this state transition table to calculate the next state of the system, right? So in the design of the More FSM, if you remember, we had the register here, we had this next state combinational logic unit, and we had some inputs, and then we had this as the feedback from the current state to the circuit, to the combinational logic circuit that calculates the next state, right? So we want to find out this part of the circuit now. So as you can see, we have some inputs here and we have some outputs. So we need to find the truth table to be able to come up with the Boolean equation that show the relationship between the output and the input. So as you can see here, this table, this transition table, kind of resembles a truth table because we have TA and TB as the inputs, and also we have the current state too. So if I divide this into two parts, the left of this red line are basically all the inputs to this next state combinational logic circuit, and the part to the right of this line are all the outputs. But you cannot draw the Boolean equation simply from this table. And the answer and the reason for that is these names that we put for our states. So these are abstract names, right? I put S0, S1, S2, and S3. I could have just easily put any other name that I wanted, right? So we cannot use these abstract names to come up with the Boolean equations. Remember, for the truth tables, we needed to have zeros and ones. So this state transition table is not helpful for writing the Boolean equation. That's why we need to come up with some Boolean or some binary values that represent these abstract state names. And that is what we want to do for the state transition table, and we want to come up with the encoding. So basically some binary values that represent these individual states or these abstract names. So since we have 4 states, the binary values that we require to represent these should give us these 4 possibilities. So the easiest encoding that we can come up with is a 2-bit encoding. We assign S0 to be equal to 0, 0. We assign S1 to be equal to 0, 1. We assign S2 to be equal to 1, 0. And finally, we have S3 to be equal to 1, 1. As you can see, we follow an order going from S0 to S3. We start from 0, 0 to 1, 1. Right? So that is what is called a binary encoding, because we follow the order of these states to represent them with some binary numbers. So this is very important. There are different types of encoding that I will go over later on, but for now we work with the binary encoding. So now that we have this binary encoding, let's just rewrite the state transition table. And the procedure for that is very straightforward. So let me just quickly go back. We had S1, S0, S2, S3. So this one was supposed to be S1, this row. S0, S2, this one S0, S2, S3, and then finally S2 and S0. So S1, S0, S2, S3, S2, S0. So S1, S0, S2, S3, S2, S0. Okay. So as you can see, each one of these state names or a state is now represented with 2 bits. So anywhere in our table, in our state transition table, when we have S0, we just represent it with 0, 0. Anywhere we have S1, we represent it with 0, 1. Anywhere we have S2, we represent it with 1, 0. And anywhere we have S3, we represent it with 1, 1. So since we use 2 bits to represent these 4 states, it's only natural to basically assume 2 bits for the register. So if I redraw this, for this specific circuit, we have this next state, combinational logic circuit. We had 2 inputs. It was TA and TB. And now we have 2 states as well. So this clock, this one is 2, and also the inputs needs to be 2 as well. So what are these 2? S1 and S0. So we have 2 bits to represent these 4 states. So that means that this register is actually, it contains 2 D flip-flops that basically get the same clock. So now, going from the state transition table to an encoded state transition table is very straightforward. When you come up with the binary encoding, then you basically just replace everything. Anywhere you see S0, you just replace it with 0, 0. Anywhere you see S1, you replace it with 0, 1. Anywhere you see S2, replace it with 1, 0. And anywhere you see S3, you replace it with 1, 1. So here we had S1, so that means it's equal to 0, 1. We have S0, that is 0, 0. We have S2, that is 1, 0. We have S3, that is 1, 1. We have S2, that is 1, 0. And finally we have S0, which is 0, 0. So the result of creating this encoded state transition table is basically a truth table that we can now use to come up with the Boolean equations. So if I rewrite it nicely, This is the encoded state transition table. So on the left side of this line, we have all the inputs to this next state logic unit, and on the right we have all the outputs. So all the inputs include the traffic sensors as well as the current state of the system. All the outputs are the next state of the system. So now that we have this, we can come up with the Boolean equations for these outputs. So you might ask, how can we do that? The answer to that is using all the techniques that we described in the previous component of the course, in the combinational logic design. We used product of sum of product, K-maps, and we did all different types of simplifications. So all of those previously taught concepts can be considered here too. Of course, one thing that you might notice here is that the order of this table, let's say we have 4 inputs here, we expect to have 16 possible combinations. So the order of these may not be the same as you saw before, or this table may not contain all the possible combinations, right? So that is good and bad. It is good because not containing all the possible combinations means that our tables are usually very smaller, right? But at the same time, that can be a little bit challenging, especially when you want to do simplifications. So you need to pay closer attention to what terms you have and what terms you don't have. So my suggestion is that the basic approach that you need to follow is by using the sum of product, which is very straightforward. If you want to get the most simple equation, you use K-maps. But you want to get the most straightforward answer, use the sum of product. It makes your life much easier. So let's just use sum of product to come up with the Boolean equations that show the relationship between these outputs and the 4 inputs that we have. So I start with S1 prime. So if you remember from before, we said that for sum of product, we look for rows for which the output is 1. And then we write the associated min term for each one of these individual rows. So let's just see what we have for this row. For this row, S1 is 0, S0 is 1. So whenever a variable was 0, we had that variable with a bar on top of it. Whenever we had a variable with value 1, we had the variable itself. And also whenever we have variables that are don't cares, we basically don't include them. So the first term for the equation, for the Boolean equation of S1 prime, is S1 bar S0. The second term is S1 S0 bar. So S1 S0 bar. TA is don't care, so we don't include it. TB is 0, so we have TB bar. That is the second term. And then finally, we have this row in which S1 is 1. So we have S1 itself. Then we have S0 being 0. So it is S0 bar. TA is don't care. And TB is 1. So we have TB. So this is the Boolean equation that we have for S1 prime. So you might look at this and realize that, okay, these two terms can be simplified. If I factor out S1, S0 bar, and then we end up with TB bar plus TB. So this, we know that it is 1. So this whole equation is simplified to S1 bar, S0 plus S1, S0 bar. And then you know that this is equivalent to having S1 XORed with S0. So these are all the follow-up steps that you can follow to get to the most simple equation. But the most straightforward answer is using the sum of product. So by simply using the sum of product, you can come up with the equation that shows the relationship between the outputs and the inputs. Let's just do the same for S0 prime. So S0 prime only has two terms. The first one is S1 bar, S0 bar, TA bar. Again, following the procedure for the sum of product. And then we have this one, this row, which is S1, S0 bar, TB bar. So plus S1, S0 bar, and then TB bar. So this equation is the Boolean equation that shows the relationship between S0 prime and all of the inputs to this next state logic circuit. Also, as you can see, this thing cannot be simplified any further. So this was how to use the sum of product form to get to the Boolean equations. If you want to do it using K-maps, what you basically need to do is to create the K-map. So here, since we have 4 inputs, we need to write a 4x4 table. So we have S1, S0 here, and then TA, TB representing the rows, S1, S0 representing the columns. Then we had to use the gray code 0, 0, 0, 1, 1, 1, 1, 0, and then 0, 0, 0, 1, 1, 1, 1, 0. And then we basically fill out this table, considering all these don't cares, and also some cases that may not be even included in this table as don't cares. So let's just see what we have. For example, let's just say for S1 prime, we have 0, 0, 0, don't care, it is 0. So 0, 0, 0, 0, and also 0, 0, 0, 1. So these two cells are 0. So we have 0 and then 0. Then we have 0, 0, 1 don't care is 0. So 0, 0, 1 don't care is 0. So these two is again 0. Then we have 0, 1 don't care is 1. So 0, 1. Whenever we have 0, 1 for S1 and S0, and for values for A and B is not important, we have 1. So that basically is all these 4 cells. Then we have 1, 0, don't care 0. So 1, 0, don't care 0. So that becomes this cell and this cell. So 1, 0, don't care 0 is going to be 1. So 1, 0, 0, 0 is 1. 1, 0, 1, 0 is also 1. Then we have 1, 0, don't care 1 to be 1. So 1, 0, 0, 1, 1, 0, 0, 1, which is this cell is 1. 1, 0, 1, 1 is 1. And finally we have 1, 1, don't care, don't care. So 1, 1, all of this is going to be 0. And then we follow the procedures as we saw before. We create circles of size of power of 2. We make sure these circles are as large as possible. And then we make sure that we account for all the ones in the table. And for each one of these circles, we write the associated implicant. And if we do that, for these two, we basically get this equation. So as you can see, using K-maps can be a little bit more challenging and involved. But the good thing about using K-maps is that we get the most simple equation. While for the sum of product, we get the most straightforward answer, even though that may not be the most simple equation. So these are the two equations that we come up with after converting this encoded state transition table into Boolean equations. So now you might say, okay, we are kind of halfway through the procedure. So in the more FSM, we had this thing. So this one was the output logic. This one is the next state logic, right? So we found out about this. We also found out about this one as well, right? Because based on the encoding, we realized that we need to have 2 D flip-flops inside this register. So what is left is basically this output logic. So for the output logic, we basically follow the same procedure as the next state logic. So since we already came up with the encoding, we use that encoding. So anywhere we have S0, we use 0, 0. Anywhere we have S1, we use 0, 1. Anywhere we have S2, we use 1, 0. And anywhere we have S3, we use 1, 1. For our output logic or our output table, what we had was that depending on the condition or the state of the system, we had some lights to be either green, yellow, or red, right? So we had 3 possible combinations for the lights. So since again we have these 3 abstract names, in order for us to be able to come up with the Boolean equation, we need to consider an encoding for the outputs as well. So not only we have the state encoding, but also we may require output encoding too. So the encoding that I considered here is for green to be 0, 0, for yellow to be 0, 1, for red to be 1, 0. Now, based on the state transition diagram, we can fill out the output table too. You remember when we were at the state 0, LA was green. So that means that the 2 bits that I consider for LA to be both 0. Again, you see, we have to have 2 bits to represent these 3 colors, right? At least we need 2 bits. With 2 bits, we can have 4 possible combinations. So we only use 3 of the possible combinations. But we cannot go below 2 bits because using 1 bit, we only can represent 2 possible combinations. Either that bit is 0 or 1. So for a state 0, LA was green, so 0, 0. LB was red, so 1, 0. For a state 1, LA was yellow, so it was 0, 1, while LB was still red. For a state 2, LA was red, so we have 1, 0. LB was green, so 0, 0. And finally for state 3, we had LA to be red, 1, 0, and LB to be yellow, so 0 and 1. So now if you look at this table, we don't have any abstract names, neither for the states nor for the outputs. And also to the left of this line, we have all the inputs for the output logic unit, and to the right we have all the outputs. Again, we can use sum of product, product of sum, K-maps to write the equations for the output logic unit. So again, going with the sum of product is the most straightforward way. So for each one of these outputs, I can use the sum of product to come up with the equation. So we have for LA1, these two rows for which the output is 1. So the associated mean term for each one of these rows is, for this one, it is S1, S0 bar, S1, S0 bar, plus S1, S0, S1, S0. So if I factor out S1, we have S0 bar plus S0 equals S1, because this is basically 1. Let's just do the same for LA2 or LA0. We have only one term, so that is S1 bar, S0. We have LB1. We have these two rows for which the output is 1. So that is S1 bar, S0 bar, plus S1 bar, S0. So now if I factor out S1 bar, so I get S1 bar multiplied by S0 bar plus S0. This is 1 again, so this is S1 bar. And then finally we have LB0, which is only 1 for this row, and this is equivalent to S1 and S0. So these are the 4 equations that show the relationship between the output encoding and the current state of the system. So again, you can use Carnot maps to basically come up with the equation. You can use the product of sum or sum of product. If you use the Carnot map, especially for this one, since we only had 2 inputs or 4 possible combinations, using Carnot maps was not that beneficial, because even by using sum of product and if necessary some simplification, we could come up with the simplest equation, right? But if you have more than 2 current states or more than 2 bits for the current state and much more complex outputs, you can use Carnot maps to come up with the simplest equations. So now that we have done everything, that is the time for the last step that we needed to have. So we want to come up with the schematic of the circuit. So what we do is that we first put the register. We signify the clock with the triangle. We provide this reset as the input. So even though we didn't consider this reset or how this reset works, we just put it like this. And what happens when you use this reset is that you basically put your system into a state 0. And if you remember, a state 0 was when LA was green, LB was red, and for the state encoding it was represented as 0, 0. So whenever you reset this system, S1 and S0 both become directly 0. And it doesn't matter whether you use synchronous or asynchronous resettable D flip-flops, right? In the grand scheme of things, those two both behave the same way. Of course, if you use asynchronous, that means that when you provide this reset signal, instantly the output goes to a state 0. If you use a synchronous one, on the next edge of the clock that happens. But nonetheless, the procedure is very straightforward. So now that we have put this, we need to put the next state, logic unit or combinational logic unit to the left, and the output here. So the output logic unit here. So we have TA, TB as the two inputs, and also we have the current state of the system as the two inputs that come from the left side of the next state logic. And for this one, we basically create LA, the signals for LA and LB. Of course, since each one of them had 2 bits, so this is basically LA1, LA0, this one is LB1, LB0. But nonetheless, this is basically the same basic design that we had for the more FSM. So it was something like this. So we had some inputs, some outputs, a next state, output, and then we had this clock that was connected to the register. So going from this basic design, or going from the equations that we came up with to this, is pretty straightforward. On the left side, we implement the equations that we had for the next logic unit using the Boolean function that we came up with. And on the right side, we use the Boolean functions that we came up with and create the schematic. So as you can see here, this is basically the next state. And this one is the outputs. So I won't go over the detail of this implementation, because by now you should know how you go from the Boolean equation into implementation using logic gates, right? So this is a more straightforward implementation. You can use a 2-level implementation too. Again, if you don't know how to do it, I highly suggest you refer to the previous videos that I talked about this. So this is the final step in the design process of a more FSM. I know it was a more involved procedure, but if you think about it, this is the procedure that you basically do whenever you want to solve a large problem too. You usually break it down into smaller steps, and then you do it step by step until you solve the whole process. So the same is true here too. We have some abstract ideas in our head, but we want to make a bunch of gates to implement or perform those ideas. So we need to design our system in such a way that those mindless components can understand it. So that means that we break the problem into smaller chunks, we solve them, we kind of transform our abstract idea into something that some mindless electronic components can understand. And then we do the implementations. So here is a basic timing diagram of the system. So we have this clock signal that is basically going between 0 and 1 indefinitely. At this point, we reset the system. So when we reset the system, we know that the system goes into a state 0. So this is basically the current state of the system. So as a result of this, we basically go to a state 0 and then we start reading for the inputs. So in this state, as long as we have traffic, the next state would be again a state 0, and the values for LA is green and for LB is red. So now you see, since we have the traffic sensor TA to be 1, we stay in this state. Right? So as long as this is 1, we stay in this state. As soon as we don't see any traffic in path A, then this triggers this transition. The next state would be going to S1. So we stay basically on the edge of the clock, we go to S1, and then we stay there until the next edge of the clock, which kind of triggers, we conclude that the next state would be S1, so this is still not being stored in the system, right? So this is S prime. So we have S prime. On the next edge of the clock, this next state would be saved into the current state. So this is the current state. This is the next state. And then when this happens, we know that since state 1 didn't require any inputs, our next state would be to go to S2. So this is what you see here, but this is still not our current state, right? In our current state, we still are at S1, and that means that LA is going to be yellow instead of green. And then on the next edge of the clock, we go from S1 to S2. Since, as you can see here, TA is now 0 and TB is 1, right? And if you look closely in this area, you see that how we gave preference to TA because of our design. When we are at the state 0, we only care about the value for TA. So even though the value for TB changed from 0 to 1, nothing happens. But as soon as the value for TA goes from 1 to 0, then we start the process of going to the next state. And then you can follow this path again to see how we basically start from this reset or S0 state and then go through each one of these individual states, giving these values for TA and TB. So that is all I had to say about the design of more FSM, and that is something that you need to always follow step by step. So if you look closely, you cannot switch different steps. So you cannot come up with the encoding before writing the state transition diagram, right? So as for the encoding, what we used was, for this specific example, we just said that we have the state and we use the binary encoding. So let me just write this again one more time. So we said we have S0, we make it to be equal to 0, 0. We have S1, 0, 1, S2, 1, 0, and S3, 1, 1. So we said that since we have 4 states, we need at least 2 bits to represent these 4 states. But the adjective is at least 2. Basically, we need at least 2 bits. So nobody prevents us from using more than 2. So what if I say instead of 2 bits, I want to use 4 bits? Like this. So let's just say I use state S0, S1, S2, and S3. And then encoding, I do it like this. I just say this is 0001, 0010, 0100, and 1000. So again, this is a valid encoding. As long as you don't have 2 states that are represented with exactly same encoding, that is fine. And that is what is called a one-hot encoding. So in a one-hot encoding, one of the bits is 1 per state, right? So this is again what is called as the one-hot encoding. So the only difference between these two is in the number of bits that we use for encoding, which translate to the number of flip-flops that we need to use for storing these encoding. So for this one, since we only had 2 bits, we only need to have 2 flip-flops. For this one, since we are using 4 bits, we need to have 4 flip-flops. So depending on the different conditions or the different requirements of the problem, some of these might be preferred, right? So depending on the question, you might be asked to use a binary encoding or a one-hot encoding. Of course, for one-hot encoding, you need to come up with more number of Boolean equations, but at the same time, generally speaking, these equations are much simpler to be represented. But again, there is no preference which one you choose. It all depends on the problem statement that, or all on the component that you have access to. So this is a quick note on state encoding. So to recap, we have binary encoding, which is the simplest form in which you use the minimum number of bits that you can use to represent the number of states that you have, and you basically go through them one by one in order, right? Or you can have a one-hot encoding in which you use 1 state bit per state, and only 1 state bit is high at a time. So since we cannot be at 2 multiple states at once, that is basically saying that only one of these state bits is 1 at a time. You cannot say the same thing for the binary encoding. For example, for S3, both of these state bits are 1, right? So using one-hot encoding, you need more flip-flops, but usually the next state and output logic equations are simpler for when you use one-hot encoding, but you have more of those simpler equations. So you have to keep that in mind as well. So in the next videos, we will go over the difference between more FSMs and mealy FSMs, and I will show you more examples on how to decide which one to choose.